Hello everyone, welcome to my YouTube channel. I am Manasa Essa, studying in Sri Venkateshwara College of Engineering from 6M ISC. The subject is software testing. Today I am going to discussing about overview assumptions in fault-based testing. Overview assumptions in fault-based testing. The contents are overview assumptions in fault based testing, mutation analysis, fault based adequacy criteria, variations on mutation analysis, test execution. Overview. Understand the basic idea of fault-based testing. How knowledge of fault model can be used to create useful tests and judge the quality of test cases. Understand the relational of fault-based testing well enough to distinguish between valid and invalid uses. Understand the mutation testing as one application of fault-based testing principles. Now, instead of bowl of marbles, I have a program with bugs. I had 100 new bugs. Assume they are exactly like real bugs in every way. I make 100 copies of my program, each with my 100 new bugs. I run my test suite on the programs with seeded bugs, and the tests reveal 20 of bugs. What can I infer about my test suite? Now let us know about assumptions in fault-based testing. We would like to judge effectiveness of a test suite in finding real faults by measuring how well it finds seeded fake faults, valid to the extent that the seeded bugs are representative of real bugs, not necessarily identical. Example, black marble are not identical to clear marbles, but the difference should not affect the selection. Example, if I mix metal ball bearings into the marbles and pull them out with the magnet, I don't learn anything about how many marbles were in the bowl. Now let us see mutation testing. A mutant is a copy of a program with a mutation. A mutation is a syntactic change, a seed bug. Example, change I less than 0 to I less than or equal to 0. Run test suite on all the mutant programs. A mutant is killed if it fails on at least one test case. If many mutants are killed, infer that test suite is also effective at finding real bugs. Characteristics of a project. Every project has 4 basic characteristics. First one is investment pattern, second one is benefits or gains, third one is time limit, and fourth one is location. In short, the project is an economic activity with well-defined objectives and having a specific beginning and end. It should be amenable to planning, financing and implementation as a unit where both cost and returns are measurable. A well-planned project includes a correct consideration of alternative, identification of key issue, compactness, enforceability, etc. It should be neat, clear cut and specific. Fault-based adequacy criteria. First one is competent programmer hypothesis. Programmers are nearly correct. Real faults are small variations from the correct program. Second one is coupling effect hypothesis. Tests that find sample faults also find more complex fault. Mutation operators. Syntactic change from legal program to legal program. So specific each programming language. C++ mutations don't work for Java. Java mutations don't work for Python. Examples. Constant for constant replacement. For instance, from x less than 5 to x less than 12. Relational operator replacement. For instance, from x less than or equal to 5 to x less than 5. Variable initialization elimination, changing int x equal to 5 to int x. Test execution. Test execution is the key to testing. Execution matrices and sequencing can help to improve efficiency of execution as does the whole testing planning. Test environments need to be planned and managed. Test data is a part of the test environment and many changes environment data procedures need to be understood to manage the impacts to the test results. Test matrices provide information to manage the test activities. Test reports communicate the outcome of a testing activities. Regression testing is used to verify new releases of software. Variations on mutation, weak mutation. Problem. There are lots of mutants. Running each test case to completion on every mutant is expensive. Number of mutants grows with the square of program size. Approach. Execute meta mutant with many seeded faults together with original program. Mark seeded faults as killed as soon as a difference in intermediate state is found. Without waiting for program completion, restart with new mutant selection after each kill. Statistical mutation. Problem. There are lots of mutants. Running each test case on every mutant is expensive. It's just too expensive to create n square mutants for a program of n lines. Even if we don't run each test case separately to completion. Approach. Just create a random sample of mutants. Maybe just as good for assessing a test suite. Provide we don't design test case to kill particular mutants, which would be like selectively picking out back marble anyway. If bugs were marbles, we could get some nice black marbles to judge the quality of test suite. Since bugs aren't marbles, mutation testing rests on some troubling assumptions about seeded faults which may not be statistically representative of real faults. Nonetheless, a model of typical or important faults is invaluable information for designing and assessing test suites.